welcome to AP Physics Podcast. This is Chapter 10, question number 27. We are asked to show that if the density of the Earth is given as a function rho of r, as seen right here, trying to show that our moment of inertia ends up being 0.330 mr squared. So we're trying to prove that this is the moment of inertia of the Earth, where m is the total mass of the Earth. We're given the hint that our moment of inertia for the hollow sphere is this right here, 2/3 mr squared, and that's given a uniform density. That's how we proved that originally. So we can see then that if we take the integral of di's, we find that our total moment of inertia is equal to the integral of all of our miniature moment of inertias. And since di dm is equal to 2/3 r squared, when we take the derivative of this with respect to m, we see then that our di is equal to 2/3 dm r squared. So we're trying to find our total integral of this, which is given by the equation 2/3 dm times r squared. Now the concern is trying to figure out what our dm is, and so in order to do that, we have to understand that our density function gives us our dm. So because rho is equal to our mass divided by our velocity, we see that rho times our dv is equal to dm. If we take the derivative of that with respect, take dm dv or dv dm, however you want to think about it. In that case, if v is equal to 4/3 pi r cubed, our dv is equal to 4 pi r squared dr. That's what we see right here. So then our dm, our little minuscule change in mass, is given by the equation 4 pi r squared times rho dr. As we set that up in the integral, we find that our integral is given by this right here. We have our 2/3, which continues from this right here, our dm, which we just solved for right here, as well as our rho and our dr, and this r squared comes from this r squared up here, and we change the notation to be a little bit more consistent with what we are looking at. We're integrating over a small r, as r goes from 0 to the total radius. When we plug in our function for our density function, we end up getting this right here, and it looks like a rather messy integral, but if you just keep your eye on the prize and go straight forward with your integrals, this whole term that has to do with the 0 goes away, and we're left with this right here. It does not simplify very well. It simplifies to this still somewhat nasty term down here, but we'll see what happens to that in just one second. If we're trying to prove that our moment of inertia for the Earth is given by 0.330 mr squared, that means if we take our I and divide it by mr squared, as you see right here, we should get 0.330. Now that involves coming up with an expression for the total mass of the Earth. Well, we have the density of the Earth, so if we integrate our individual dm's here, we should be able to get the total mass of the Earth. And so that's what I did right here. Our mass is equal to the integral of dm, which is the integral from 0 to r of our dm function. Our dm was given up front here as 4 pi r squared times rho dr. So when you integrate that, you get this still somewhat nasty value for m, but now you see that a lot of those nasty functions that were up here in our I expression are repeating again in our m. And as we divide those, we end up having an r to the 5th over an r to the 3rd, so we end up with our r squared. This term, the 14.2 over 5 minus the 11.6 over 6, ends up simplifying a little bit as we cancel out those values down here, the 14.2 and the 11.6. We're still left with our fractions, but it's much nicer down here. We can come up with a common fraction between these two. And after some simplification, we do end up coming up with the ratio gives us 0.330. So that then tells us that the total moment of inertia of the hollow sphere given by the Earth is 0.330 mr squared.